Hello everyone, today I will be presenting my paper, Data Driving Analysis and Machine Learning for Energy Prediction in Distributed Photovoltaic Generation Plants, a case study in Queensland, Australia. This research was conducted by me, Lucas Ramos, supported from Marilene Colnago and Wallace Casaca. We came representing the São Paulo State University, UNESP. As we know, the availability of energy has been one of the key aspects to ensure a sustained economic expansion for human development. The use of non-renewable energy resources has been a faster and cheaper way to guarantee such economic progress, but with an inconvenient price of keeping pollutant emissions rates high. Aiming at trying to overcome this issue, several countries have gradually incorporated renewable energy resources into the power matrices, once ensuring a trade-off between economic growth and energy security in the future. Among these resources, photovoltaic energy has gained more and more space and investment, especially because of its versatility of installation, free use, and abundance of solar radiation in several countries over the globe. Considering the scientific literature on photovoltaic energy generation and distribution, the use of computational intelligence has emerged as a trend, which includes accurate predictive models based on machine learning paradigm. In fact, these models have contributed to an increase in reliability and safety when supporting decision-making. For example, predictive models can be successfully used to identify small power oscillations caused by external factors in photovoltaic systems, thus ensuring better predictability of electricity generation and dispatch. Aiming at assessing and forecasting the energy charge in distributed photovoltaic power plants, this paper proposed the studies, analysis, and application of machine learning pipelines on different data profiles from houses and businesses in Queensland, Australia. The proposed method consists of three main steps. Initially, data collection, processing, and analysis, then organize, train, and tune the machine learning models, and finally, apply the models to test data for target prediction. The data were collected from the PV output platform, and cleaning and analysis was performed using the KDD process. The chosen models were random forest, gradient tree boosting, and support vector machines, being widely used in applications like this one. The training of the models was carried out with a ratio of 1:3, where we had 3 years for training and 1 for testing. The models were tuned using the random search strategy, seeking to replace grid search with a better cost-benefit ratio. The data used in your analysis consists of 20 individual datasets, each one representing an energy data profile shared by an active user on the energy management platform called PV Output. The data shared in this open repository gathers real cases of energy generation and dispatch, as effectively managed by consumers and suppliers of solar energy. The selected region was Queensland because of its large amount of data available to conduct this study, allowing us to explore a more complete database holding long-term data, 4 years. The data instances include, among several features of power generation and distribution, generated energy, efficiency, exported energy to the grid, peak generation, climatic conditions, and the minimum and maximum weather temperatures. As the first step of the predictive modeling, we conducted the knowledge and data discoveries (KDD) process analysis to detect specific patterns among the data that could be used to improve the performance of the forecasting models. As a result, new combinations of energy-related features were originated from the raw data, making these artificially created variables indispensable for the success of training step of the models. As stated previously, the original data include generated energy, efficiency, exported energy, peak generation, climatic conditions, and minimum and maximum weather temperatures. And after applying the KDD process, the following complementary features were added: generated movement average, generated movement subtraction, exported movement average, exported movement subtraction, with a window size of 2, and finally the average temperature. 3 machine learning-based approaches have been prototyped and properly optimized. The following algorithms were chosen as baseline when designing our learning pipelines: random forest, gradient tree boosting, and support vector machines. As we can see, the random forest and gradient boosting models are ensemble types, and the support vector machines is based on supervised statistical learning. Random forest is a learning methodology that relies on the combination of weak learns to deliver a more constant process of learning. It employs an effective procedure of randomization when selecting noodles in the decision trees so that it causes the algorithm to assign greater weights to the variables that most influence the prediction. Gradient boosting takes a learning premise called boosting strategy, which consists of training several submodels with handle subsamples during the training step. Combination then to obtain a less particularized performance with less overfitting. While in bagging, the weak learns are trained in parallel using randomness. In boosting, the learns are trained sequentially. Supervised machine learn is a kind of machine learn where the machine learns from labeled data to create a model. Depending on what you want to predict, supervised learning can be used to solve two types of problems: regression or classification. In this algorithm, we plot each data item as a point in any dimensional space where n is the number of features you have, with the value of each feature being the value of a given coordinate. Then we perform two classification or regression, finding the hyperplane that best differentiates the two classes. In regression, epsilon was a function to give a tolerable error on the regression model. It depends on the problems. If we need a higher tolerable error, we can increase the epsilon intensity band and vice versa. On the figure, we can see an example of support vector machines applied to linear and nonlinear regression. Mean absolute error is the average of errors in our measurements. It is the difference between the measured value and the true value. Root mean square error is the standard deviation of the prediction errors. It is a measure of how spread out these prediction errors are. The mean absolute error and the root mean square error can be used together to diagnose the variation in the errors in a set of forecasts. The root mean square errors will always be larger or equal to the mean absolute error. The greater difference between them, the greater the variance in the individual errors in the sample. The mean absolute percentage error, MAPLE, is a measure of how accurate a forecast system is. It measures this accuracy as a percentage and can be calculated as the average absolute percentage error. Here, we start by inspecting the correlation among the following photovoltaic variables: generated energy, exported energy, generated energy moving subtraction, and generated energy moving average, and conditions, weather conditions. From the first row, we can see that there is a high correlation between generated energy and climatic conditions. As the weather plays a fundamental role in the power generations, sunny and cloudy days tend to have more radiation than rainy days. The second row emphasizes the correlation between the exported energy with the other features. Firstly, we can be verified that generated energy holds a high dependence on the exported one, as the amount of energy dispatched to the power grid is always a portion of the photovoltaic energy generated. Moreover, from the third and fourth rows, both artificially created variables, generated energy moving subtraction and generated energy moving average, are highly correlated to generated and exported ones. This confirms that the newly created features are capable of positively influencing the general accuracy of learning models. Figure 4 presents the observed and predicted data for generated and exported energy concerning a regular user profile, dataset number 1, over the first week of 2020. We can check that the three trained models were able to capture the real data for both modalities of energy charges, producing accurate estimates over the period. Another aspect to be noted is that generated energy is rarely correlated to exported. We can see in the data trajectory in Figure 2a and Figure 2b. The accuracy metric computed for each photovoltaic dataset is plotted in Figure 5. In the generated prediction, the models produced accuracies greater than 94% in the measured of cases. Despite the high accuracy, the predictors dropped in performance on the same datasets, which may be related to the high deviation in these variables understood for these particular datasets. Considering the plot in Figure 5b, the models performed similarly well in the most cases. However, the accuracies were lower than generated energy. In fact, this can be explained due to the dependence among the features. While the generated electricity is more influenced by climatic conditions, the exported load is more dependent on the factors such as energy consumed and the ratio exported-generated. Those values cannot be included as part of the prediction pipeline because they are computed using the target variables. Concerning the quality metrics in table, notice that all the predictions obtained by the trained models achieved MAPLE scores lower than 5%, except that one delivered by the support vector regression for exported electricity. These errors measurements confirm the high performance of the trained machine learning models for the task of predicting both generated and exported energy from distributed photovoltaic systems. In this work, we apply and tune several data-driven strategies to explore the distributed photovoltaic energy as a case study in Queensland, Australia. This included data-driven tools to investigate the relationships among different energy-related variables, as well as the implementation and tuning of 3 machine learning-based models. Despite the good predictability, the models were less assertive for exported load when compared to the generated energy, a fact that can be explained by the dependence of variable exported with the generated one. Even so, the largest MAPLE was around 6% considering all predictions computed, a satisfactory error considering the large size of forecasting windows. Among the 3 evaluated models, gradient tree boosting was the one that achieved great compatibility with the predictions of both targets. Finally, the implemented models proved to be robust and stable when applied to different photovoltaic datasets. Thanks for everyone's attention. It was a pleasure to participate in this event. This research was being supported by São Paulo Research Foundation, FAPESP, and São Paulo State University.